Let's take a few minutes and look at the solutions to the probability multiple choice practice questions. So question number 1, you flipped a fair coin 5 times and the first 4 flips land heads. What's the probability of heads on the 5th flip of the coin? Well, the coin doesn't realize that it's shown heads 4 times in a row. So the likelihood that the next flip lands heads is still 0.5. It's still 1/2. So the coin doesn't have any memory. So under the condition that we've already shown heads 4 times, that condition of 4 previous heads is irrelevant. The next flip is still 1/2. The 5th flip is independent of what's happened on the previous 4 flips. Question number 2. So this is a good review question because really this isn't a question so much about probability. It's a question about the shape of the normal distribution. Now remember, the normal distribution we can use to find percentages of outcomes, and we can use those percentages of outcomes to represent probabilities. So let's draw a picture of this. So we have a variable with a mean of 100, a standard deviation of 10, and we want to know which of these expressions down here is equivalent to the probability of x is greater than 115. So let's draw a picture of what x is greater than 115 looks like. So here's the normal distribution. Here's the bell curve. So I know the mean in this case is supposed to be 100. I know the standard deviation is, in this case, I believe it was 10. So, and we're looking for the likelihood of an outcome of 115 or higher. So 115 would be right here. We're interested in this percentage of observations. That's going to represent for us the probability that our outcome is greater than 115. And what we need to take advantage of is the symmetry of the normal distribution. So notice here at 115, we are 15 units above the mean. So this percentage will be the same as the percentage of 15 units below the mean. So if I put my boundary at 15 units below 100 or 85, I know because of the symmetry of the distribution, the percentages of observations below 85 is the same as the percentage of observations above 115. So in terms of probability notation, this is the probability that x is less than 85. So that's the answer that we're looking for here. Let's go back to the quiz. There we are. It's the probability that x is less than 85. So something to think about. We're going to need this not only on the final exam, but we'll need this within our next unit and also going forward. This is the question in terms of the actual mean and standard deviation for the problem. We could also rewrite this in terms of z-scores. So if you wanted to work with z-scores have a mean of 0, and they have a standard deviation of 1. And if I wanted to turn this 115 into a z-score, I could just use the z-score formula. This is the z-score formula. So that observation of 115, if I want its z-score, I just need to subtract the mean of 100 and divide by the standard deviation of 10. That's going to give me a z-score of 1.5. So we could even write this probability in terms of z-scores if we wanted to. The probability that our z-score is greater than 1.5. And that would, by the symmetry of the distribution, that would be the same as this 85 is 1.5 standard deviations below the mean. That's what a z-score means. So the alternative probability, the expression that will have the same probability is then the probability that z is less than negative 1.5. So we can express this in terms of actual observations, or we could express this same situation in terms of z-scores. So question number 3, this is about trying to determine the likelihood of a particular flight. So understand that our probabilities don't represent what happened in the short run. Probabilities for us represent what happens in the long run. So if we look at many observations of exactly this flight over and over and over again over a very long period of time, that's what this probability of 0.7 represents. So understand, though, that we have to represent the probability by looking at this particular flight over and over again. I don't care about all airline flights. I don't care about extended weather forecast. So this is the correct answer here. On all previous days, this particular flight had been scheduled. It had arrived on time about 70% of those days. That's our best estimate for the true probability. So it's not about all airline flights, and I don't need to make a bunch of crazy assumptions. For our purposes, the law of large numbers in this case says that over time, as this flight occurs more and more and more times, the actual percentage of the time that this flight is scheduled, the percentage of the time that it arrives on time in the long run, approaches its real probability. And in this case, that would be 70% according to the question. So question number 4, in this question, it would have been helpful to watch the video about the relationship between mutually exclusive or disjoint events and independent events. So in this case, we know A, B, and C, those outcomes are mutually exclusive, so they are disjoint. And I have to figure out which of the following is true. So I know that number 1 is not true. If events are mutually exclusive or if they are disjoint, I know that they are dependent upon one another. So 1 is not true. Number 2, if they are disjoint, A and B cannot happen at the same time. That probability should be 0. That is correct. And if they are disjoint, if I take the probability of B or C, because they can't happen at the same time, I can just add the individual probabilities. So I know here that the correct answer is 2 and 3 only. Question number 5, this is about a simulation. So I want to simulate the fact that 30% of subscribers to this cable television service watch the shopping channel at least once a week. So I am using the digits from 0 to 9. There are 10 digits from 0 to 9, so I need 30% of them. I need 3 of those digits to represent the event watching. So that would be here. I want to assign 0, 1, and 2, that's 3 of the 10 digits, or 30% of them, to be watching the shopping channel. That means the remaining digits represent someone who is not watching the shopping channel if I randomly select one of those digits. So here, in terms of this simulation, it's important that you assign your digits to genuinely represent the probability of 30% that you're trying to simulate. So question number 6, this is an interesting question because the 275 students is really not necessary to answer the question. What I care about is that 20% of them are vegetarians, and then it would really help to organize the information about these 20 people into a table, because I'm interested in whether or not they eat fish and whether or not they eat eggs. So let's draw a picture. Let's draw a diagram for this. So here, I've got 20 observations. There are only 20 people to organize into my table here. So I'll organize it this way. Fish and no fish. I guess I could write fish complement. That would be fine. Here are, they eat eggs. They don't eat eggs, so I'll write eggs complement. I know that in total, my totals will be out here in the margins. I know there are 20 people to organize here. So let's go back to the information. It says of the vegetarians, so of these 20 people, 9 eat both fish and eggs. So I know where the 9 goes, fish and eggs. So 3 eat eggs, but not fish. So eating eggs and not eating fish, here's where those 3 people go. So, and 7 eat neither. So 7 eat neither. Fish complement, egg complement. Here's those 7. Now with those numbers, I can complete the table. The 3 plus 7 makes 10. So this needs to be a 10, so the 10 plus the 10 makes 20. This needs to be a 1, so the 9 plus 1 makes 10. The total of the egg row is 12. The total of the eggs complement row is 8. And now I can find any probability I would like because I have my data organized. So what's the probability that the chosen student eats fish or eggs? No problem. So I want them to be in the fish column. So I want to include these outcomes. And I also want them to be in the egg row. Oh, but I don't want to double count this 9, so I also need to include this 3 right here. So I have 9, 10, 11, 12, 13 observations out of the 20. There we go. 13 out of 20. This is a good example of a question where organizing the information, I suppose you could have used a Venn diagram to do this. A tree would not be helpful here because I don't have conditional probabilities. I'm looking at all 20 students as one snapshot at one moment in time. So I'm just classifying all 20 of them in terms of their fish and their egg eating behavior, if you will. So a table or a Venn diagram is really the best plan there. So question number 7, what's important here is I have 2 tests for determining whether steroids have been used, and they operate independently of one another. And I want the likelihood that neither test is positive. So understand neither test being positive if steroids have been used. That's an and probability. So I want the probability that A is not positive, so A is negative, and test B is negative. So no problem, they work independently of one another, so I can simply multiply the 2 probabilities together that I care about. So here, A has a probability of 0.9 of being positive. That means that the probability of it being negative is 0.1. B has a probability of 80% of being positive. That means that its probability of being negative is 0.2. And if I multiply those together, I get 0.02. That's the probability that neither test is positive. That's the probability that both of them are negative. This question is a clever little question because it relies on independence, and it also relies on the general addition rule. So I want the likelihood that test A or test B is positive. So let's organize this one in terms of the general addition rule here. So I want the probability of A or B. Well, in general, I can add the probability of A to the probability of B, and then I want to subtract off the probability of A and B. Well, I know that the probability that test A is positive if steroids have been used, that's 0.9. I know the probability that test B is positive, that's 0.8. Now, they could both be positive, and because they are independent of one another, I can simply take the probability that A is positive times the probability that B is positive. So remember, when events are independent, this and probability, the probability of A and B, when they are independent of one another, it's simply the probability of A times the probability of B. So I can take advantage of that shortcut to find this probability here. So I have 0.9 plus 0.8 minus 0.72. This is 1.7 minus 0.72. That gives you 0.98. So if you take both tests, the likelihood that one of them, A or B, the likelihood that one of them is positive is relatively high. That's 0.98. The remaining questions then are involving tables. So here, if this die is thrown and the top face shows an odd number, so that's my condition. What's the probability that the die shows a 1? So what I'm trying to calculate here is the probability that we show a 1, given that I know that the number is odd. So what you could do, you could simply look at the odd outcomes, 1, 3, and 5. So I'm interested in the probability of a 1, so that's my numerator of 0.3. So, but the denominator is what's possible. So what's possible is only an odd outcome. So the odd outcomes have a total probability of 0.3 plus 0.1 plus 0.1. They have a total probability of 0.5. So the probability of the odd outcomes is the 0.5, but the probability of a 1 and an odd outcome, of course, if it's a 1, it's also odd, that probability is 0.3. So it's relatively easy to see what I want just from the table, and if I reduce this, 3/5 is simply 0.6. So that was the answer that we were looking for in this question. So questions that involve tables are pretty important. So here's our last two table questions, and I don't want you to work too hard. What's the probability in this case that the GPA is under 2? Well, that's the total of this column here, and that would be a total of, in that case, 255, but it's out of the total of the table, and you didn't have to total it up because it tells you right here that there are 1,000 students. So this is 255 out of 1,000. That's the probability of a GPA under 2. So that's 25.5%. So here's question number 11. Question number 11 is a conditional probability. What's the probability that a student has a GPA of under 2, given that he or she has skipped many classes? Well, if they're in the many classes row, there are a total of 110 observations in that row, the skipped many classes row, and 80 out of those 110 have a GPA under 2. That's 80 out of 110. So let's write those two probabilities down together so that we can compare them here. So the previous probability was the probability of having a GPA under 2. And that was, if I remember correctly, that was 255 out of 1,000. So that probability is 0.255. And we just found the probability of a GPA under 2, given that they've skipped many classes. So we found that probability in the table as 80 out of 110. So I'm going to turn that briefly into a decimal here so that we can compare them. Always write your probabilities as fractions. Writing them as decimals is useful for comparing. Of course, if the question says write it as a decimal, please do that. But if you need to make a comparison, it's really easiest to do that with decimals. So this is 0.727. So the reason that I wanted to do that involves the last question. So the last question, I know the probability of a GPA less than 2, given that they skipped many classes, is higher than in general the probability of a GPA that's less than 2. Actually, it's quite a bit higher. The probability, if you've skipped many classes, the probability of a GPA less than 2 is about 73%, 0.727. Overall, the probability of having a GPA that's less than 2 is only 25.5%. It's only 0.255. So understand the condition that someone has skipped many classes, that definitely has an impact on the probability of a GPA that's less than 2. Given that a student has skipped many classes, it definitely increases significantly the probability of a GPA that's less than 2. So because there is an effect on the event GPA less than 2, these are not independent events. They are dependent events. Skipping many classes affects the GPA. So having a GPA that low depends on how many classes you've skipped, whether or not you've skipped many classes. So in this case, these are not independent events. Another way you could say that is that these events are dependent. So those are the answers to the 12 practice multiple choice questions.